Here we are asked to determine the number of oxygen atoms found in 7.50 moles of diphosphorous pentoxide. Since we have prefixes associated with our elements, we know we are dealing with a molecular compound, so everything on the right of the stair step on the periodic table. And we also have to recall that di is a prefix that means 2, and pentoxide or penta is 5. So I'm dealing with a diphosphorus, which is 2 phosphoruses plus 5 oxygens. Now, those prefixes are actually going to be the subscripts underneath each element. So it's going to be P2O5. And from this, I can go and determine what my molar mass is or my atomic mass. However, I don't really need to because I know how many moles of this compound I have. I have 7.50 moles of P2O5. And all I'm doing is converting the number of moles of this molecular compound into atoms of a particular element inside. So the first thing that I could do is actually divide or multiply this by Avogadro's number to get to the number of P2O5 molecules. So for every 1 mole of P2O5, I'm going to multiply this by 6.022 times 10 to the 23rd P2O5 molecules. So my moles are going to cancel, leaving me with a number of molecules. So if I was to take this diphosphorous pentoxide and break this up into oxygens, if I was to take P2O5, just 1 molecule, I would get 5 oxygens out of it. So if I was to break up 1 mole of that molecule, I would get 5 moles of that oxygen. So my amount of molecules are going to break up. And in this case, I already dealt with the moles previously because I did Avogadro's number, so that should have been molecule. And now I have 5 oxygen atoms. So from this, I'm going to get a value of 2.25825 times 10 to the 25th atoms. And this should be to 3 significant figures, so I should produce 2.26 times 10 to the 25th oxygen atoms. And one thing that I highly stress to everyone is that I would encourage you all to start underlining the O for oxygen because it's easy to confuse an oxygen with a 0. So please underline your oxygen or put a line through a 0, whichever you can to differentiate between the two. Now, from this, I can find additional information about anything else. Let's hypothetically say that with this amount of oxygen, I want to produce a different compound. So I'm taking all of the oxygen that I could get out of that diphosphorous pentoxide and put it all in aluminum sulfate. Well, how much of that aluminum sulfate could I make? So I'm starting with 2.25825 times 10 to the 25th atoms of oxygen. The question is, how do I deal with my aluminum sulfate? Well, there's 2 compounds. I either have a molecular compound or an ionic compound. Aluminum sulfate is ionic because I see a sulfate, and sulfate is a polyatomic anion. So aluminum is Al3 positive, and sulfate is SO4 2 negative. So you do this, I call this a charge shuffle or an ionic shuffle, where every superscript becomes its neighbor's subscript. So the 3 in Al3 positive will be a subscript for the SO4. And the 2 in SO4 becomes a subscript in my aluminum. So I'll have Al2 parentheses SO4 out of parentheses 3. Now, these set of parentheses are very important because it's signifying that I need 3 of the sulfate ions to do this balancing. That, if you would have left it as Al2 SO4 3, first off, you would, if you can even do that, you're putting a parenthesis around the 4. That means you have 12 oxygens. And you just can't multiply that out to Al2 S3O4, S3O12. You need to signify that you're increasing the number of sulfates, not just the individual atoms. So while the S3O12 might look correct in terms of the molecule, we want to keep it to balancing out the ionic charges. So we're going to keep it with the parentheses on the sulfate, even though we will now have 3 sulfurs and 12 oxygens. And that's the important part, how many oxygens I have in aluminum sulfate. Because based on the number of oxygens I have, I will convert my atoms of oxygen to my molecules of Al2SO4 3. So if I break up 1 aluminum sulfate, I would need 4 times 3 oxygen atoms to do this. So my oxygen atoms cancel, and then I can convert my number of molecules dividing by Avogadro's number to get moles. So 6.022 times 10 to the 23rd molecules will be on the bottom, and 1 mole on the top. So my molecules of my aluminum sulfate cancel, leaving me with a mole, and the value that I would get from this is 3.125 moles of Al2SO4 3. The answer should be to 3 significant figures. So the rule of thumb is if you have to round from a 5, if you round from a 5 and there's nothing else behind the 5, you round to the closest even number. So this will be 3.12 moles of aluminum sulfate.